Hey everyone, and welcome back to another session from the Net Academy. I'm David Townsend, and on this session what we're going to be doing is going into the OSPF designated router or DR and backup designated router. And we've gone through a lot of information so far. We've gone into the different OSPF packets, we've gone into the adjacency states, we've gone into the different types of area types and what LSAs you should see or maybe not see in those specific types of areas. But now we're going to be focusing on why we need a DR, why we need a BDR, and what benefits they actually bring, and of course how to configure those on a Juniper Junos device. So let's get going. So here we go, here's the network, and as you can see it's not a very sophisticated or large network. We've got simply a virtual switch right in the middle, which is just providing access to 4 VMX routers, and at the top we've got router R1 with router ID 1.1.1.1, R2 with router ID 2.2.2.2. Guess what? R3 is 3.3.3.3 and R4 is 4.4.4.4. But why do we need a designated router? Well, in this kind of topology, it's obviously not very big, is it? But let's say, for example, we've got another router here, and we've got another router here, and another router over here, and another router over here, so on and so forth. Oh, my map has gone off there. But say, for example, you've got 10 routers in total. So 10 would be the total number of routers in your OSPF routing domain. Now that doesn't sound like a lot, but don't forget with OSPF the routers have to build an adjacency to one another, and whilst 10 doesn't sound like a lot, when it comes to the adjacencies they have to build to each other of those 9 routers, it actually really adds up quite quickly. And there's actually a calculation to do this. So if we do n with in brackets n minus 1 divided by 2, this is then 10 minus 1 divided by 2, so we then have 10 times 9 again divided by 2, and obviously right at the end we'll come out with 45. So what that means in English is that for 10 routers in a single OSPF routing domain, they would have to build 45 hopefully fully connected adjacencies to one another. And that has a big impact, because if you think that if R1 has got a link flapping going up and down, up and down, up and down, it's got to send those link state updates, those link state updates, those link state updates all the time into that OSPF routing domain. And every other router has then got to run that shortest path first based on the Dijkstra algorithm to update their link state database, and that will take a certain amount of CPU cycles. So the whole idea of having a designated router, and what we're going to do in this lab is have router R1 as the designated router and R2 as the backup designated router, is that we're actually going to limit the amount of adjacencies that are built from routers to the DR and to the BDR. So all other routers, which are neither the designated router or the backup designated router, they are known as DR others or druthers. However you want to pronounce it, it really doesn't matter at the end of the day. But we've got a designated router and a backup designated router. Now the druthers will build a full adjacency to both that designated router and to that backup designated router. But from druther to druther, they do not build that full adjacency. They only get maximum up to that 2-way adjacency. And that's important because they are not then sending those link state updates to other druthers in there. It all goes via that designated router, and if that goes down, that backup designated router. So in short, why do we need a designated router and a BDR? Is to prevent the amount of adjacencies that are really needed in a broadcast network. And this is really what we're talking about here, is that this is a broadcast, or it can even be a non-broadcast, but it is a multi-access network. We are really limiting the amount of adjacencies that have to be built, and thus if there is an update, the amount of CPU cycles that is consumed on a per router device. But how do we actually elect a designated router or a backup designated router, or even a druther? Well, what we've got is priorities. So you have a priority value which is, and this is an important point, which is per interface. And what this allows is for you to do is to configure a specific priority on that interface, which would be a 0, which is the absolute minimum. In Junos world, 1 to 8 is the default, and 255 is absolutely the highest that you can configure. So first, if you've got a priority of 254 on router R1, this means that this is pretty high, and this is what we're going to actually configure as the designated router. We could see router R2 has that priority of 255, so this is absolutely the highest, and we're going to actually configure this as the backup designated router. Down here, router R1 has got that priority of 1, sorry, R3 has got that priority of 1, which means that this is going to be a DR other, and router R4 has that priority of 0. So those are the priority values, but what happens if there's a tie? So say you've got two routers and both of them have this priority of 255 or whatever it may be, they've got the same priority. How are you going to have a method to break that tie? Well, what that then comes down to is what router has the highest router ID. So if we look up here, if this wasn't 254, say this was 255, it would have the same priority as router R2. So which one then would become the designated router? Well, in such a case, it would be R2, because router R2 has the highest router ID of 2.2.2.2, whereas R1 has an ID of 1.1.1.1. So that is how you actually break a tie. At this point, you might be thinking, though, well, hang on, Dave, you've said that we are going to configure R1 as a designated router, but it actually has a priority, or it will have when we configure it, a priority of 254. Whereas on R2, which is going to be the backup designated router, it has a priority of 255. We could see that 255 is the highest, and thus 255 is lower. Well, why is R2 not going to be the designated router? That's actually a good question if you're asking yourself that. And that is because in OSPF for designated router and backup designated router, it is non-preemptive. What that means in English is if, and we're going to do this on the lab so you can see this, is when we boot up R1 and for it to start participating in OSPF, it is going to be sending out a specific type of packet. We'll come on to that in just a second, but it's going to be sending out these packets to discover, is there anyone else out there that's already a designated router or a BDR on this route, on this in this subnet, in this broadcast, non-broadcast, multi-access network? Is there anyone else out there? And it will do that for 40 seconds. And if it doesn't hear from another router saying, yeah, I'm the DR or I'm the BDR for this multi-access network, it is going to assume that there's no one else out there, there's no other routers out there, and it's going to elect itself as that designated router. But when BDR comes into it, when R2 is then configured into OSPF, and we're going to do this even with a higher priority, and it sees R1 is already here as a designated router, it is not going to take over that designated router role. It will elect itself as that backup designated router. And it comes back to this saying, if it's not broken, don't fix it. If the DR is there and it's working, it's sending out the link state updates to the druthers, etc., then why would you want a router to take that functionality away? So it's non-preemptive. So when router R2 is configured into OSPF, it is not thus going to take ownership of that DR row. It will become the BDR. The only way it would become the designated router is if R1 was to fall off, go completely off the network, power down, disconnected, etc., and then router R2 would become that designated router. And when R1 comes back into it, it would then become that backup designated router. So the next question is, what OSPF packets carry that information about that designated router and maybe the backup designated router? The answer is that, let me just select my pen. The answer is the OSPF hello packet. And as I mentioned, it will send when we configure R1, it's going to be sending out OSPF hello packets for the first 40 seconds. Now this is known as that wait timer. It's also the same time as the dead interval on OSPF. So for the first 40 seconds it's going to be sending out these hello packets, and in here it's going to be saying who is the designated router, and we're going to see it's going to say 0.0.0.0, i.e. I do not know who that designated router is. It's also going to have a field for who is the backup designated router, and again it's going to be 0.0.0.0. It will also contain its router ID, i.e. I am 1.1.1.1, i.e. R1, and also what is my priority on the interface itself. Again, default Junos is 128, but we're going to configure it to have 254 on router R1. So it will be sending out these packets for the first 40 seconds, and when it sees that there's no other OSPF speaking router on this multi-access network, it is going to say, okay, and this is the IP address on the interface, so it will be 192.168.10.1, and the backup designated router will stay as 0.0.0.0. When R2 comes into it, it is then going to have 192.168.10.2, and this is important because then when R4 and R3 are configured to participate in the OSPF protocol and to build the adjacencies, they're going to see who that designated router is and who that backup designated router is, what are their router IDs and what their priority, and thus they can then determine and will determine that actually I'm not going to be a DR, I'm not going to be a BDR, and I'm going to build a full adjacency to that DR and BDR, and for all other DR others or druthers out there, I'm going to build that two-way adjacency. So how does all this updates take place in the OSPF routing protocol for DRs and BDRs? And what I mean by that is, how do the DR others or druthers update the designated router and the backup designated router? How does the designated router or BDR update a DR other if the update has come from another druther? And there's two important multicast IP addresses that you need to know about. That is 224.0.0.5. Now this is the all OSPF multicast IP address. What that means is without any DRs or BDRs, it is used for all OSPF routers to speak to one each other, and it's actually what the DR and the BDR use to communicate to the DR others. And then we've got a very similar IP address, 224.0.0.6. Now this is specifically for the designated router and the backup designated router. But let's take this one step further. So what happens if the designated router, as we can see here, receives an update? Now that update might be a new link coming into the designated router and it's advertising or redistributing that into OSPF, or it could simply be a link which has run out of time, it's got a bit stale in its link state database, and it needs to send that link state update throughout the OSPF routing domain. So what happens when the designated router receives an update or sends an update? First, to the 2.0.0.5 address, it is going to send a link state update, and that link state update is going to go across to the backup designated router, but it's also going to go down to the DR others or druthers. So all routers in the OSPF routing domain receive that link state update. But then router R2, the backup designated router, is going to do something. What it's going to do is it's going to say, well, actually, I am going to acknowledge that update. So it is going to acknowledge that it has received that link state update. And that's important because it allows the designated router and the DR others to see that actually that backup designated router is still there, it's still live, and it's still connected. And when that's happened, guess what? The next part, and this is all happening simultaneously, the next part is the DR others are going to send to the .6 IP address. So only the designated router and the backup designated receiver see this. They are going to send their acknowledgement up saying, I actually have received that update and I acknowledge that update back to that designated router and to the backup designated router. But what happens when the backup designated router receives an update? Well, the process is actually very similar. It's just swapped over from the DR to the BDR. So we've got an update coming in here, new link or a topology, an entry that's gone stale in the link state database needs to be updated. So the backup designator will send that link state update out to the 224.0.0.5, and this will go to the designated router. It will go down to the DR others as well. So all of these routers in that same OSPF router domain receive that link state update from the backup designated router. What happens then, and just like we saw in the first part here, but now the designated router is going to send its acknowledgement back, and again to the 224.0.0.5 multicast IP address. So it's letting the backup designated router know, as well as the DR others know, that actually I have seen this update and I am acknowledging it. I am still here, I am still connected, I am still around, I am the designated router. But of course now the designated router others, or druthers, other type of routers, however you want to pronounce it, they are going to send their link state acknowledgement, or link state acknowledgement I should say, spelled it incorrectly there, apologies, up to the 224.0.0.6. So this will then be received only at the designated router and at the backup designated router, and this is going to happen for router R3 as well. But what happens if there's an update on a DR other? So what happens if either the DR other or druthers, router R3, R4 receive an update? It doesn't really matter which one we'll go with, but we'll choose router R4. So there's a new update into router R4 here. So it is going to send out its link state update, either there's a topology change, there's an entry that I need to update, to the 224.0.0.6. Almost wrote in 5 there, but it is 8.6. Let me write it there for a little bit more clarity. So the 224.0.0.6. So it's going to send that update to the designated router and to the backup designated router. Now when that designated router receives that update, it is going to send its link state acknowledgement to the all OSPF multicast IP address 224.0.0.5, and that's going to go to the backup designated router, and it's also going to go down to the other non-designated backup and designated routers, i.e. the DR others. So even though R4 has got this topology change and this update, and it's sent it up to the designated router and to the BDR, router R3, the other druther, still gets that update. And when that update has been received at all other remaining DR others or druthers, it is then going to send its link state acknowledgement back to the .6. So then the designated router and the backup designated router know that actually all druthers in this network have got the same link state database. And remember, that's a really important part for OSPF. So let's start configuring this OSPF designated router and backup designated router and the interface priorities on the Juniper Junos devices. So first we're going to configure router R1. So I've already started up the shell, so here we are on router R1, and if I just do a quick show protocols OSPF, you could see there's absolutely nothing there. But is there anything on the interface GIGI001? Well, if I do show interfaces GIGI001, we could see it's already been pre-configured with the IP address 10.1 or 192.168.10.1 to be precise, of course. Okay, so let's set the routing protocol OSPF. And I literally just said the word there, so I'm going to do set protocols OSPF area. Now there's not an area on this lab. It really doesn't matter for this demo for this purpose because it is just a lab. So I'm just going to do area 0. Now we need to point it towards an interface. I'm going to do gigi 0/0/1.0. You don't have to do the dot unit or sub interface, whatever it may be, because Junos will automatically enter in the .0, but if it is a .1, .2, .3, it is therefore going to pick up the wrong unit. So it's just good practice to always put that .unit in there. So gigi 0/0/1.0, and now if I just enter question mark, we could see all the lists. Let me just expand this a bit more. We can see all the variables that I've got out of that question mark, and there's quite a lot here, and obviously we're not going to go through them all, but the one that we're actually concerned about for this video is the priority. So now if I define the priority, and as we can see up here, we've got a priority of 254. Now I'm not going to push commit just yet, because what I want to do is go onto the routing interface and run a packet capture. So I'm just going to select R1 capture on the capture, there we go, on the gigi 0/0/1 interface. And so here's the Wireshark capture on the gigi 0/0/1 interface. Took a few seconds to load up there, but as you can see, I'm just filtering it onto all OSPF headers and packets which are seen captured on the Wireshark. So now I'm just going to run a commit. And once that's actually come through and been committed into the running configuration, there we go, we can see already there's a few packets that we are seeing on the Wireshark. So I'm just going to go into this maximum. Oh, there we go, that's better. And we can see the first packet here, which is the one I'm looking at, is going to have the OSPF. We're going to look into the header. So the header is really talking about, you know, what area. So we know it's area 0, the router ID, packet length 44. But for this, I want to look at the OSPF hello packet. And here's the information that I was really talking about before we went into this lab. Notice the DR is 0/0/0/0, and the backup designated router is 0.0.0.0. That is because router R1 does not know yet who the DR and BDR actually is. It's just sending out these hello packets to say, hey, I'm here, here's my router ID, here's my priority, this is my area, etc. Is there another DR and BDR actually out there? And remember, it's going to do that for 40 seconds, which is that wait timer. So if we actually come onto this one, onto this packet, it might not be there just yet, but if I go onto the OSPF hello packet, and you can see it's already done it just there. So it's already elected itself as that designated router, because there is not another OSPF speaking router within this multi-access network yet. And that is where we are now going to go onto router R2. So here there's absolutely nothing configured for the OSPF routing protocol. So let me do a set protocols OSPF area 0 interface gigi 0/0/2 unit 0. Good practice. And I'm going to give this the priority of 254. And if I enter in commit now and go back to the Wireshark capture, and what we can see on the Wireshark capture on router R1's interface is going to be a bit different now. So if I just look at the latest hello packet and go into the OSPF header, the hello packet, let's maximize this. Note now, designated router is still router R1 192.168.10.1, but the backup designated router is 192.168.10.2, i.e. router R2. And that is bringing the theory into practice now, because router R1 elected itself as that designated router, and we've just configured R2 as participating in the OSPF routing protocol. Even though it has a higher router interface priority, it's not taken that DR row away from R1, because OSPF DR and BDR is non-preemptive. It's not going to take that row away unless router R1 reboots, reloads, restarts OSPF, whatever it may be, i.e. goes offline and comes back online. Now if I actually go back onto R2, here we go here, and if I do the run show OSPF neighbor, then we can see if we've built that full adjacency to router R1. And if I run the same command now, but if I go into extensive, we can see the IP address, the interface, its full adjacency, and we can actually see we've got bidirectional communication, and even now, more importantly, the priority of R1 is the 254. But let's configure R3 and R4 for participating in OSPF. So I'm going to bring these both up at the same time. So that's router R3 over here, and let me just bring up R4. I'm going to do them both at the same time. So let's do set protocols OSPF area 0 interface gigi 0/0/3.0 priority of 1, and I'm going to commit this. And if I actually enter in over here, set protocols OSPF area 0 interface gigi 0/0/4.0 priority of absolute 0, so it would never ever become a DR or BDR. It's the lowest of the actual priority values, and we can see they've both been committed. Now let me just drag these down, and if I actually enter in a run show OSPF neighbor, let's see if we've built the adjacencies. Now note, we have built the full adjacency to that designated router R1, and it's got that full adjacency. I've just noticed I did make a mistake on the priority settings on router R2. That's fine. The theory's there. So apologies, that should have been 255. It's actually 254. But for the router R2, we've also built that full adjacency. So again, that's the theory building in that the druthers will build the full adjacency to that DR and BDR, because that's where they're going to get their link state updates from. That's how they're going to keep their link state database intact. But to router R3, router ID 3.3.3.3 with the priority of 1, it has only gone up to that two-way state. So it can see it's there, but it's never really going to go past that. It's not going to go into the start state, it's not going to go into the exchange state, it's not then going to go into loading or eventually into full. It's going to stay at two-way, and as such these druthers are never going to share link state updates or even link state acknowledgements to each other. And if I do the same command and run show OSPF neighbor, we can see the same over here. But how does it look from R1 and R2? Well, let's go into router R1, and let me just drag this over here, run the same command, run show OSPF neighbor, and we can see we've got full adjacencies to both routers R2, R3, R4, and it will be the same on router R2. Let me bring up the right one here. So if I just do a run show OSPF neighbor just here, and we've got the full adjacencies, because remember, the DR and BDR build a full relationship to each other and to the druthers. It's only the druthers that do not build that full relationship to each other. And so that's the end of this video on the OSPF DR and BDR election process. We've gone into how those routers, how those roles are actually elected, the interface priority, how you can configure that on the Juniper Junos devices, and what packets, as we saw in the Wireshark capture, what packets are actually used, i.e. the hello packets, and what they actually contain in terms of who is the DR, who is the BDR, what is my router ID, and what is my priority. So stay tuned for the next video, where again on Juniper Junos devices we're going to be going into more detail, again into OSPF, but we're going to be focusing on equal cost multipath, i.e. ECMP, and within this and built around it, we're going to be going into how does the SPF algorithm actually work? What routes does it prefer? Does it prefer intra-area, inter-area? What does it prefer exterior, i.e. E2 and E1 routes over intra-area, and what those E2, E1 routes actually are? So stay tuned for the next video, and thanks for watching.